I'm just going to do a quick presentation on two methods for estimating load shift potential in commercial heat pump water heating systems, and one of them which was used in the tech program in California and estimates both the kilowatt hour energy savings from load shifting and the CO2 emissions savings. So you can go to the next slide. So I'll talk about the tech program calculator first, which this screenshot is a little bit old, so it still calls it the SGIP, Self-Generation Incentive Program, but it's being run as the tech program in California. And this online calculator was used to allocate $6 million worth of incentives to load shift capable central heat pump water heating systems in California. So those projects have applied, reserved the funding. None of them have been built yet and installed, but the program will will also have a monitoring piece so that after the installations happen, they'll be able to monitor and see how well they performed, and potentially even compare that to the calculator. And so you can this is just the kind of beginning page, how to use it. The first step, I actually had a video embedded in the presentation, but it was too big to add, so we're just going to go with the old slide method. So the first step in the incentive calculator is you put in your zip code, and that grabs weather data and CO2 emissions data for the California climate zone. So this tool is specific to California for the tech program. It was built for the tech program. And then you put in building specifications. And those are like how many bedrooms of different, how many apartments in different bedroom configurations, and it uses that to calculate the occupancy and the recirculation losses. And for the tech program, they asked us to lock it to the California spec mode in EcoSizer. And for those of you who aren't familiar, EcoSizer is also an online sizing tool that Ecotope develops. And so this page is just, it was an added page to the website. So you can size your system on one tab and then move over to the next tab and run this simulation to get an incentive. Next slide. Then you scroll down from there and you can select system configuration. And these are all the system configurations that are listed in the advanced water heating specification. And so far, kind of the most common, well, they are the most common systems installed. And so we have single pass and multi-pass, and then we have the temperature maintenance system configuration below. So you can select from swing tank, parallel loop tank, return to primary, or no recirculation. Next slide, please. Then after that, you can select from this drop-down all the heat pump water heaters that are listed in JA13 for California. And this gets you the performance map from the heat pump water heater that's used in the simulation that gets run, the annual simulation that gets run to calculate the CO2 emission savings. And then you select the quantity of heat pumps and the primary storage gallons, the swing tank element size, and the swing tank volume in gallons, and that's all the system specifications that are needed for the simulation to run. Next slide. And then here you would input the controls, the load shift controls. So for normal load up and shed, we kept it simple for the online calculator to just do normal load up shed. And for those, you select the aquastat fraction, which the heat pump turns on at, the outlet temperature of the heat pump, and the simulation will then shift the aquastat fraction and the outlet temperature based on the operating mode. in the simulation. And so then you say simulate your system. So you can keep going through the slides here. I guess, can I change the slides? Well, maybe I can.
If you take control of the top, Scott, you can change it, and then you don't have to wait for me.
Okay.
You see that button at the top?
Yeah, I'll just do that.
Perfect.
Okay.
Yeah, you got it.
So then we have, this is what the results look like. So it shows you the blue line is the energy used, average energy used for each hour of the day for the system that was load shifted, and the red line is the average energy that was used for the system that was not load shifted. And so you can see there's a little spike where the load up happens, and then it sheds through, and that grayed out period is the period in the simulation where we've chosen to tell the units to shed. So it doesn't dynamically change from day to day, but it does like kind of the best estimate based on typical hours in California. And so what this does, then it takes all of the energy used for each hour of the year, the CO2 emissions for each hour of the year, and it uses that to estimate the kilograms of CO2 emissions reduction annually from adding load shift capability to the system. And then it calculates this kilogram CO2 emissions per kilowatt hour of energy storage metric, which needs to be above 5, I believe, to qualify for the tech incentive. This is just the inputs. So we've got air temperature, water temperature, controls. We didn't include, there wasn't enough information to include defrost in the stratification profile in this simulation. So we did our best to work around it and get reasonable results. We've done some studies on both defrost and stratification. So really what we need is to find some funding to add these to the EcoSizer backend simulation, which is an open source tool. And then they could be included in future similar tools to what we developed for the tech program. So next I'm going to talk about what we're calling the NIA load shift test, which is as opposed to simulating what our load shift capabilities are going to be, we're going to test what the load shift capabilities are. And so this test, we ran it in the PG&E lab, which I'll talk about later, but it also could be part of a commissioning process where you design a system, you set up the load shift controls, and then you could go out there and measure a couple things during commissioning testing and calculate a load shift value for the installed system. So this is how it works. You would wait for the heat pump water heater to stop running in a normal setting. So no request for shed or load up with no draw on the system. And step 2 is you send a load up command to the system. No draw, you let the storage fill up to where the system would turn off in a load up state. And then step 3 is you send a shed signal to the heat pump water heating system. You induce a draw on the system based on the size of the system, which we have like a table in the test. And you track the energy that is released from the storage system into the building. And the test is complete when the heat pump water heater turns back on in shed. So essentially it gets you a delta of energy that can be in hot water that can be released to the building between the turn off and load up and the turn on and shed state. And that gets you what we're calling the thermal shift capacity. And this is just saying we could do it on site during a commissioning startup process. We could also use this same calculation methodology during an M&V installation where we just look at that delta in the data, figure out what the thermal shift capacity is. And we ran this test at the PG&E lab in California. This is just the temperature profiles of the tank during the test. Kind of cool rainbow looking plot. And then we compared that EcoSizer test methodology that I talked about first, where we used for the tech program, and this is the thermal shift capacity that is, we ran the testing in the lab in California, and we calculated the thermal shift capacity, and then we input those same systems and controls into the online simulation tool that we built. And we said, okay, we're going to just compare if the thermal shift capacities look comparable. And they do. They're pretty close. They're all within 10%, and or mostly within 10%. And I would say that that's a pretty good result for us. And then we also, with the advanced water heating spec, have a methodology for taking that thermal shift capacity and the system specs and using it to extrapolate to both what is the electrical shed capacity, which will be different based on conditions, and what's the peak load reduction, which would also be different based on the outdoor air conditions. So the peak load reduction, we would look at the performance map table in the advanced water heating spec and find basically what is the input power for the outdoor air temperature in that, which correlates to the season in that climate zone, and that gives us an estimate for this resource of a heat pump water heating system. What is the kilowatt instantaneous power reduction that we'd be getting by shedding it? So in this performance map we're looking at for one heat pump, not sure which model this is, it looks like in the coldest times of the year, we get 17 to 19 kilowatt reduction in the warmest time. So in the summer, we get a 12 kilowatt reduction. So basically, it's not as large of a resource in the summer as it is in the winter because it's operating more efficiently. It has a higher COP. And so that's for the peak load reduction. And for electrical shed capacity, what we do is we take the thermal shift capacity and we divide by the COP. And so what our methodology for doing this is we say in the advanced water heating spec, there's 4 different climates. There's cold, mild, and hot climates. And so there's 3. And so what we're doing is I believe there's also a very cold, but we're using the cold for both of those. So the very cold, mild, hot. So there's 4. And so we're saying for cold climate and very cold, we'll use the 5 degrees COP, and the thermal shift capacity divided by that COP is our electrical shed capacity. So now this is the total number of kilowatt hours in energy that this resource gives you as a reduction in energy usage during a peak period at different temperatures and climate zones. So you can see that since the COPs are higher in the summer electrical shed capacities are lower. That makes sense. And yeah, this is just the one of the big things here is that kind of what we've been able to do is essentially tie together funding and insights from agencies in the Pacific Northwest and agencies in California to create kind of a system for estimating load shift capacity using the advanced water heating spec and the SGIP tool and comparing them and trying to kind of find out, okay, everyone's looking for the same goal, right? Everyone's after the same goal, which is to understand how well this technology is going to perform as a resource for load management at a utility level. And so let's see if we can take what all these different ideas and kind of find a unified approach. And so I feel that we've been able to at least get a start on that, and there's still definitely more work to do, and also some work to validate this method. But I think we've been able to kind of take it a step in the right direction and get people aligned. So that's all I had.
Nice work, Scott. Do we have any questions?
Oops.
One question I had, Scott, I have not been tracking the Caltech program. Was that application submission that you talked about at the beginning, was that for calendar year 23 or was calendar year 24 done also?
Are you talking about the tech program?
Yeah.
That was calendar year 23 that all the applications were sent, but it was at the end of 23.
Hmm. Any other questions, thoughts? I mean, that's a really, I think I like to see the amount of potential there. So I've always said, like, you know, if we're looking at one residential unit or 100 residential units, and then we're looking at, you know, a large multifamily building, the energy shift potential is more easily, maybe, let's say, controlled, right?
Yes, yeah. And you have a smaller electrical connection to start with, and you get to take advantage of the diversity of the usage of all the tenants. So one person using a lot of hot water while another person doesn't use hot water doesn't cause one system to kick on. So you have a cleaner ability to shed for a longer period of time.
Mhm. Thank you.